Okay, so I'm back. We're going to record a lecture here. Hopefully, I'll see everyone on Friday. As you guys watched from your recording last week on Friday, we got into chapter 3 of the textbook, which is all about mechanical properties of materials. As I mentioned, material properties determine how a material deforms and fails. And obviously, this is incredibly important in mechanics of materials because obviously we're looking at what the material properties are of the materials we're working with in order to determine design strengths and deflections and how ultimately this material is going to deform underneath the loading that we calculated and determine, and you guys learned how to determine from statics. And so as we went through a few key vocabulary terms, which we'll talk about a few more of these as we continue on, I gave you this YouTube link, which I think is incredibly useful. They go through, it's a real quick 6-minute video talking about all of these little bits of vocabulary and some of the ultimately the tensile test, the tension test is what they call it. So one of the big things you get from a tension test, which a tension test, if you did not watch the video, is essentially taking a specimen and placing it between two plates. And you anchor it to 2 plates, and we kind of saw this in our chapter 1 discussion on stress and shear stress, and we kind of had 2 boards that were glued together and we were pulling them apart. That's essentially a tension test. You take a specimen of a known material. In this case, maybe you wanted to take steel and a certain steel grade, and you wanted to pull it apart. And so we take a piece of this material of a known diameter, and you can see 2 specimens there on the right. Those are pictures of them. And you anchor them at the top and bottom. Usually you thread the material like you can see here. Thread the material to anchor it on both ends. The threading is also larger in an effort to localize the failure between the 2 plates. So you would have some threading going on up here. We'd thread this into our machine, and we would take this machine and we would pull our specimen apart. So we put in our material for our tension test. Okay. So we put in our material and we do our tension test. During this test, we're measuring 2 different properties or parameters. Okay. We know that we are going to know the diameter of our specimen, right? So looking at our 2 specimens, pictures of our 2 specimens there, right? We could measure the diameter. That would give us our area. And then we know a known force, right? We would have a force, say F, that we are applying. We would be measuring this force. So we essentially have force over area or stress, right? So we could be essentially calculating what our stress is at any given moment in our material as we are conducting our tension test. And then strain, similarly, right? We're going to know what our original length is, right? This would be L. And as we apply our forces, right, these 2 plates are going to pull apart, right, and our specimen is going to be elongated, and that elongation, right, is our delta that we talked about before, right? This is delta, and that delta, excuse me, I'm trying to get over this here. Our delta over L, right? Delta over L equals epsilon, or our strain. And so we can calculate the strain in our specimen as we continue to apply load. So we plot this stress strain curve, right? Stress in the y-axis, strain on the x-axis, and we get a graph. And that graph tells us a lot about our material, okay? And we gain a lot of information about it. So if we looked at our 2 specimens, okay, the pictures that we see at the top, this picture on the left, you can see this cone failure. Well, this is indicative of a ductile failure mechanism, okay? On the other end are a flat, granular, no necking, right? You can see some kind of necking down of our specimen here as it gets narrower. At that necking down is non-existent in what we would call our brittle material, right? And so if you look at our two stress strain diagrams, right, our brittle material really doesn't undergo a lot of deformation, right? This would be epsilon brittle, where our ductile material can undergo a lot of deformation. Before failure, right? Before they fracture. Okay. One of the biggest things, well, I guess before we move on to the next page, right? So we have a brittle material and a ductile material, and we had this parameter or this vocabulary called toughness, right? And toughness is the ability to contain or absorb energy under this, and so it's essentially the area under our stress strain curve. So for our brittle material, right, it does not absorb or contain as much energy as a ductile material. Or you might say that this ductile material is tougher than our brittle material. Okay, it doesn't mean it's stronger, but that means that it's tougher. Another key vocabulary term, right, our Young's modulus or our modulus of elasticity is our measure of stiffness okay. Sorry, I gotta start a timer, otherwise I'm gonna go too long. Measure of stiffness. Well, our Young's modulus or modulus of elasticity is essentially the slope of our elastic portion of our stress strain diagram. Okay, so that would be this portion right here, right? Or this portion right here of our stress strain diagram. Okay, so it's our measure of stiffness, right? So E, which stands for our modulus of elasticity, is our change in stress, change in sigma over our change in strain or change in epsilon. Okay, so for each of our materials that we tested, right, our brittle material and our ductile material in our tension test, okay, each of them has a modulus of elasticity or a stiffness, right? In this case, our brittle material, right, would have a modulus of elasticity that is higher than our modulus of elasticity for our ductile material, right? Because the slope of our brittle material elastic line is steeper than our ductile material. Right, so we would essentially go out, right? We're plotting our stress and strain, right? Delta over L. And we would choose a point out here, right? We'd call it epsilon 1, sigma 1, right? Out on our stress strain diagram, that's part of our linear portion. And we would say that our modulus of elasticity is our change in sigma over change in epsilon. Or we would say sigma 1 minus 0, right? We're going to start at the origin. That's where our tension test starts, right? We've induced no force. We've induced no deformation into our specimen. It's at 0 stress, at 0 strain. So we start at 0, 0, and we go out to some stress and strain, right? So our change in stress is essentially 0 out to our stress 1, and our change in strain is 0 out to our strain 1. So we get a stress over strain, which if we look at units, right, we have PSI, we have megapascals, pascals, talked about our metric units. For strain, we have a unitless number or meter over meter, inches over inches. Okay, remembering that a Pascal equals a Newton per meter squared. So that is how we would calculate our Young's modulus or our modulus of elasticity, which will end up being, right, because if we have a unitless number dividing out our PSI or megapascal, we have E is essentially in PSI, sometimes in KSI, right? 1,000 PSI is a KSI. We've got megapascals or even gigapascals for our units. Right? So knowing E and knowing, say, the strain, we could figure out what the stress was, right? Along this linear portion, knowing that it's along the linear portion. As we go beyond that and it becomes nonlinear, then this equation doesn't hold true, right? Because we're outside of the curve, we're outside of this straight line. But if we're in this region, the highlighted yellow region, and we were given a strain, we could figure out a stress. All right, let's look at some of the regions of our stress strain diagram. Okay, in this case, we're likely looking at, say, a steel specimen or similar metal. Okay, we have this elastic behavior, right, which we just talked about. This is where we get our Young's modulus or our modulus elasticity or our stiffness of our material in our linear elastic. They'll call it our linear elastic region. That's essentially saying, right, if we're in a tension test, right, we've got our two blocks and we've got our specimen spanning between it. Right, it's anchored into our blocks and we start pulling this specimen apart, right, doing the tension test. So we start at 0, right, and we start loading up our material, right? We start pulling it apart, we start adding force, F. If we add force, we're starting to add, whoops, I need to learn how to do a delta. That is not right. We add delta, right? Or a change in length. And we know that our original length was some distance L. Right? So we start pulling this apart. We start at 0, 0, right? 0 stress, 0 force, and 0 deformation or 0 strain. And we start pulling on this tension specimen and we start running up this elastic curve, right? And we continue to go and go and go until at some point we hit this point called yield, right? We hit this point of yield. What is yield? Well, yield is where the material then will exhibit a constant stress with increased strain, right? So essentially it'll continue to elongate under the same amount of load, right? So if I gave you a round piece of steel, okay, bar stock, maybe it's 1 inch in diameter, we put it in this tension test, right? We fix it on both ends and we start pulling it apart. We are going to increase the force, and there will be a point where, say we get to 100,000 pounds, and that bar, if we just continue to make sure we have 100,000 pounds on it, okay, that bar will continue to elongate without being able to carry any more load, right? If it was able to carry more load, it would stop deforming, right? But in this case, when a material yields, it'll continue to deform under the same amount of stress. So we hit this yield, and then at one point what we end up getting is we get so much deformation in our material that it actually changes the structure of the material. There's a crystalline structure of steel, for instance, right? All of the molecules and atoms are aligned in a certain way. Well, if you start deforming it to a certain extent, it will actually start the process of what we call strain hardening. So under enough deformation or enough strain, it actually hardens the material and strengthens it. Okay, so if we continue, wrap the corner here, yield, right? We continue, we got to a certain load where it just started stretching without adding any additional load. Well, at some point that's going to stop. We're going to have to continue to add additional load for it to deform more. Well, this is called strain hardening. Okay, what does this mean? Well, this means that you need to increase stress to increase strain. Okay, we'll call this area 1, we'll call this area 2, we'll call this area 3. And you continue to increase stress, right? So we're continuing to increase the force that we're pulling this 1-inch bar apart with. And increasing that force, we're gonna essentially continue to pull it apart more and more. Okay. At some point though, we're gonna get to our ultimate strength. Right? We call this sigma U. It's our ultimate stress. At some point we're gonna get to our ultimate strength, right? That's the ultimate amount of stress that our bar can handle. And we get to that point, then we get into the range of the area we call necking. Okay, we'll call this area 5. Okay, necking. Well, what is necking? Well, you could see it with our brittle material or our ductile material, right? A brittle material doesn't have this big bench and behavior that we saw or that we're seeing in our diagram we're going through, right? The brittle material goes up, yields slightly, and then breaks, right? Doesn't have a lot of toughness, doesn't have a lot of area under the curve, doesn't have a lot of ductility. Ductility meaning a lot of deformation to failure, right? That it doesn't go very far in the strain diagram. So if you look at our ductile material, we get this area right here, right? That's smaller in diameter now. That's because it has reached beyond its ultimate and it starts what we call necking. What does necking mean? Well, that means that the area goes down. Because our ultimate stress is just that, our ultimate, meaning that's the most load that our 1-inch rod could handle. Well, once it reaches that point and we continue to add additional loading, right? Well, what ends up happening is our stress goes down because the area of our material starts to neck down, right? It can no longer handle any more stress. And so in order to maintain that force, it ends up necking. So it reduces its area. So we call this the necking. And then at some point, it gets to a point where we hit our fracture stress, right? What we call here, this is our ultimate strain, or epsilon U, call this region 6. So that would be our fracture stress. At some point, it becomes, it goes beyond its ultimate, strain capability, and it fractures, just like you see here in our picture. Okay. Now we're going to look at, this is a stress strain aluminum. Okay, this is a stress strain diagram for aluminum. All right. And in our example up above and all of our previous examples, we just loaded this one way, right? We just put our specimen into our testing machine and we started pulling on it. And we just continued to pull on it and pull on it and pull on it until it ultimately fractured. Well, at any given point along this line, we could then unload our specimen, right? We could turn the machine off or unload it and see what our behavior is. And so in this case, okay, that's what we did with this piece of aluminum. Okay, so we start at 0, 0, always starting at 0, 0, right? 0 force, 0 strain. We start at 0, 0. We start loading up our specimen. Okay, this is our elastic behavior, right? Region 1. Then we hit our yield, right? Constant stress with increase in strain, that is region 2. Then we start getting some strain hardening going on, right? An increase in allowable stress with an increase in strain. And then what do we do out here? Well, right here at this point, we decide to unload our specimen, right? Reduce the force that we're putting on it. And so when we do that, okay, our material is going to unload, right? We're going from a, say, sigma 1 down to sigma 0, right? This is 0 stress. Well, this always follows our modulus of elasticity. Okay? So we load up our material, we go through region 1, our elastic behavior. We go through yield, it strain hardens, okay? But after it strain hardens, or even after it yields, at any point along this curve, if we decide to unload it, it's always going to unload along the same linear line or slope as our elastic behavior section. Okay, so it's going to unload at that same slope. So we unload it, and if we go to reload it, it's going to do the exact same thing, and it's going to come right back and yield back into the strain hardening line. Finally getting up to ultimate strength, right? This would be sigma u. Going through necking, right? That's area 5, and then finally to fracture at area 6. One piece of vocabulary is what is called the proportional limit. And this is the stress where our stress strain curve is no longer linear. All right, so at what stress does our material essentially start to yield, right? It starts our region 2. And this is our proportional limit, right? The stress and strain are no longer proportional to each other, so that's the limit to that proportion, right? One doesn't follow the other in proportion. This isn't a linear line anymore. And that's what you would call our proportional limit. We use that to decide, at what point does our yielding start for our material, which is important. All right, we're going to start through some examples so that you can see what you can use our stress strain diagrams for and how important they are. Okay, so if we look at elastic and plastic behavior, we look at an example, right? So we have a 1-inch or a 100-inch bar, right? So that's the length of it. Our 100-inch bar is subjected to the loading pattern illustrated. Right? So as I mentioned, you don't necessarily always have to undergo a tension test where we say just continue to pull the bar till fracture. We could pull the bar, you could have a different sequence. You could pull the bar, say up to here, unload the bar, down to here, reload the bar, up to here, back down to here, back up to here, and continue to do this sequence, right? Knowing that once we get past our elastic and get into our, what we would call inelastic, right? We're putting permanent deformation into our bar, right? Because anytime we get off this linear line, right? When we unload it, we unload it back to 0 deformation, right? We're going to have some amount of permanent delta, right? Permanent deformation. And so that sequence matters on how we go about determining kind of what the performance of the bar was, what ultimately the behavior of the system is going to be. So we have an example. We have a 100-inch bar. It's subject to the loading pattern illustrated. Okay. And we want to determine the length of the rod before reloading. Okay. And we also want to know what the proportional limit before and after loading is. So I did the first section for you. Okay. So the solution would be a 100-inch bar is pulled past the initial elastic strain as stress increased above 43 KSI, right? 43 KSI. Okay, is the breaking point between our linear elastic region and our yielding region, and began to permanently deform, right? So once we get past point A, we are permanently deforming our bar, because if we unload it, right, we're going to come back linearly in our same slope as our modulus of elasticity. So when unloaded, the strain reduced proportional to stress via the modulus of elasticity, right, as I just mentioned. Just prior to reloading, the permanent set strain dictated the bar length. Right, so if we load it up to B, we decided to unload it, okay, and we get back down here and we set at point C. So when we go to reload, we're already going to start at a strain. I'm going to say that this strain equals 0.0055 inches per inch, right? Well, we know that strain is delta over L. Well, that's essentially saying that our delta, or our change in length, is our strain times our original length. We know our original length is 100 inches. Okay, and we know what our strain is at point C, right? That's the permanent strain that we've induced into our material after unloading. So that would be our delta. And our length of the rod before we load is going to be our original length of our rod plus our delta, right? Our delta is a factor or a function of our permanent strain, which we've determined as 0.0055. So we have 100 inches, our original length, plus our 100 or 0.0055 or our 0.55% strain in our 100-inch bar. Well, that gets us a permanent length of our bar before reloading as 100.55. Now, if we decided to reload our bar and we reloaded it up to, say, stress B, okay? If we reloaded it up to stress B and decided to unload it again, we would come right back down to point C. We would need to reload to B plus some strain, right? We'd have to reload all the way out to here before we would gain some additional permanent deformation in our bar. Second part that they liked us to determine, right? Part B. Part B, they want to know what's the proportional limit before and after loading. Well, this proportional limit, as I just mentioned, is that difference between or is the point between where our behavior of our specimen changes, right? It's no longer proportional. There is no proportion between stress and strain. So it's essentially no more linear. It's no longer linear between stress and strain. And so you have, right, point A would be that initial point. That's the point where the linear line no longer is linear. We get into this inelastic strain region, right? So before we determined that would be 43 KSI. So we would say before our proportional limit was 43 KSI. Well, after we loaded it up to point B and then unloaded it, right? and then we reload it again. Well, now our linear elastic portion for our material, the performance of our material in the linear elastic region, right, it grew. We now have this longer linear line, and now B, the stress at B, is our point of inelastic strain, right? Right, the bar is going to act elastic along that whole long length up to B. And so our proportional limit is essentially our stress at B, which in our case is going to be, right, 60 KSI, or stress at B, right? And this was our stress at A. So that's our proportional limit. All right, let's do another example. So in this case, we were given a portion of the stress strain curve for a stainless steel alloy in the figure. We took a 350 millimeter long bar, and it's loaded in tension until it elongates 2 millimeters, and then the load is removed. And they want to know, what is the original yield stress using the 2% offset method? What is the permanent set in the bar? What is the length of the unloaded bar? And if the bar is reloaded, what will be the proportional limit? All right, so let's start this, right? Oops, find, not defined. Solution. Okay. So, solution, part A, they want to know, what is the original yield stress using the 0.2% offset method? Well, what is the 0.2% offset method? Well, as we can tell from some of our other curves, right? If we look at this, for instance, our yield area, or our area 2 of our stress strain curve, right? It's hard to really attach a specific value for yield stress, because in that region, right, in this region, there's some variation in stress, right? It's no longer proportional, so we pass the proportional limit, right? The curve bends over because we no longer can increase stress, right? At a given stress, we just increase strain. It just becomes taffy, right? You just pull on it the same amount of force, and it continues to elongate, right? So in order to really classify what a material's yield strength is, what they've done is come up with a rule, a general rule, and it's called the 0.2% offset method. And they say that essentially the yield stress that you would use is based on a 0.2% offset, or a 0.002 strain offset of your linear elastic line. So we take our linear elastic line, right, this portion for our stainless steel, and we decide to offset it by our 0.2%, or 0.002. So what do we do there? We essentially draw a parallel line to our linear elastic region that's at a 0.002 strain, or a 0.2% strain, or a 0.2% offset. And that classifies our yield stress, right? Because it's hard to classify exactly what the yield stress is for this material. It's constantly varying. It's relatively flat, but this method allows us to provide a specific yield stress that in general captures what our yield stress is for the material that we're testing. So in our case, what is the original yield stress using the 0.2% offset method? Well, in this case, if we look at this graph, I'm going to say that sigma y, or sigma yield, equals 440 megapascals. Okay. Next question they ask is, what is the permanent set in the bar? Well, we need to know exactly how they decided to load this, right? Well, the original length of the bar was 350 millimeters long, and they said they loaded it in tension until it elongates 2 millimeters, and then the load is removed. Well, we know the original length, right, L, was 350 millimeters, and we know delta, they just said, right, they elongate it to 2 millimeters. When they want to know what is the permanent set in the bar? Well, the permanent set in the bar trying to double check here. Okay. Trying to make sure I can follow this correctly. Okay. So we know that our strain in the bar, right, is delta over L. We know we have 2 millimeters. That was our deformation. Our original length of our bar was 350 millimeters. So we have a strain in our bar of 0.0057 millimeters per millimeter. Well, where's that at in our curve? Well, that's really close to right here, right? Okay, so this would be 0.0057. Okay, so we took our bar, we loaded it until it elongates 2 millimeter, and then the load is removed. And they asked, what is the permanent set in the bar? Well, if the load is removed, we know that our ultimate strain, or not our ultimate strain, but the strain that we induced in the bar, right? We just calculated it as 0.0057. So we followed this curve, out to that point. Well, they told us that the load is then removed. So we are going to come right back. Parallel to our linear elastic, right, modulus of elasticity, because the load is removed. So our permanent set in the bar right, is at a strain right, we'll say strain permanent equals 0.0035 millimeters per millimeter. Right, if we wanted to figure out what the permanent elongation of the bar is, we would essentially say, right, our delta equals epsilon L. Well, that equals 0.0035 times 350 millimeters. calculate this, is 1.225 millimeters. That's the permanent deformation, right? Our permanent strain is 0.0035, which resulted in a permanent delta of 1.25. Well, part 3, it says, what is the length of the unloaded bar? Well, we know that our permanent deformation in our bar is 1.225 millimeters. So our permanent length of our bar, or the length of our unloaded bar, is our L plus delta, right? 1.225 equals 350 1.225 millimeters. Part D, if the bar is reloaded, what will be the proportional limit? Right, well, the proportional limit, as we know, is where it changes from there being a proportion or a linear relationship between stress and strain. Well, if we unload it, we're going down this linear line. If we reload it, we're going to go right back up this linear line until we hit our stress strain curve, right? And then we're going to start going along it. So that would be our proportional limit. That's where it's no longer proportional between our stress and our strain. So in our case, this would be, say, 460 megapascals. So we're going to say 460 megapascals. Hope that all makes sense. All right, let's do another example. Okay. We have another stress strain curve. Okay, they're giving us our complete stress strain diagram, and then they give us an enlargement of the linear portion of the stress strain diagram. Okay, so they're going to take out essentially, let's see, it'd be 120. They essentially take out 120, this section of the curve, and they blow it up. And that's what we see at the bottom. And for this material, they want to know, what is the ultimate strength of the material? What is the yield stress of the material using the 2.2% offset method? And what is the modulus of elasticity for the material? Right? Pretty fascinating, right? We take a specimen, okay, we put it in this machine, we pull it apart, we get this curve, and from this curve we can get so many properties from the material that we'll then use, which we'll talk about later on, we'll then use to relate back to design, right? Because we know what a material can handle, you know, its ultimate strength, its ultimate yield stress. We know if it's brittle, we know if it's ductile. We know what its modulus elasticity is, right? So we can design our material for a given yield stress, right? Based on a factor of safety. We can also make sure that it's stable, right? Stability is a function of both strength and stiffness. Okay, and then we also want to make sure that it doesn't deflect or deform more than we would like it to. Well, that's all a function of our modulus of elasticity, right? That's stiffness, right? How steep is that linear line, the stress strain diagram, or our modulus of elasticity, right? When we're in this region here. Steeper that line, stiffer the material, less deflections for a given amount of load, which could be desirable in certain situations. So we do this one test and we get so much information about a material, right? And that's why the tension test is one of the most predominant methods or means of classifying materials. Right? It's a really great test to induce on a new material to understand a lot of its material properties. So for this material, they gave us our stress strain curve and they want to know, what is the ultimate strength of the material? Well, this is pretty easy, right? Our ultimate is this stress way up here. Well, I'm going to say that lands at 155. So if we call this A B, and C. I'm going to say A is 155 KSI. And that's sigma U, right? That's the ultimate stress. That's the highest stress that this material reaches before failure. And they say, what is the yield stress of the material using the 0.2% offset method? Well, you can tell from this diagram, right? This material is incredibly ductile. It goes all the way out to 12% strain, right? 0.12 strain. It's so large, in fact, that we had to blow up this section to see what this plateau looks like, right? If we blew it up, right, this thing goes out and out and out forever and ever and ever, right? And it's hard to kind of see the other regions, right? We've got necking right here. We've got our fracture stress. We have our ultimate. We've got our strain hardening. And in this area here, we have our yielding. Right? And then we have our elastic. And if we load up our material and say we decide to, we load it up, continue to load it up, and we decide to unload it, right? It's going to be, well, that one's not super parallel, is it? It's going to unload at the same linear slope as our elastic region at anywhere along this curve, right? We know that now. So we blow this up so we can get a better idea of this yield region, right? Past our proportional limit. Proportional limit in this case might be right about there, is where it starts to keel over and stress and strain are no longer linear, right? So that's 1 to E. Well, we know that we use this 0.2% offset method to determine what our yield strength is, right? Our yield stress is. So we start at a 0.2% strain, or 0.002. We go up at the same slope as our linear line, and we will hit, so that's not really the same. That seems better. And wherever we hit our stress strain curve, right, following our same modulus of elasticity, we get our yield stress of the material using the 0.2% offset method as 80 KSI, right? Call that sigma Y or sigma yield. And lastly, they ask us, what is the modulus of elasticity for the material? Well, we know our modulus of elasticity equals our change in stress over our change in strain. Well, if we consider our proportional limit, right, that's the end of our linear line, and that aligns in this case with 60 KSI. If we start at 0 and we go to 60 KSI, our change in stress is 60 KSI. Our change in strain in that point just happens to line up nicely with 0.002 inches per inch strain. Well, if we go through that calculation, our modulus of elasticity is now 30,000 KSI. Which in this case is very close to what we normally always assume for steel, which is 29,000 or 30,000 KSI. So my guess is that this material is a steel alloy of some sort. All right, we're going to continue with example 3 and get a few more. me see here. Yeah. All right, so as we continue with example 3, right, so we determine the ultimate strength of the material, the yield stress of the material using the 0.2% offset method, and we determine what the modulus elasticity of the material was. Right. Again, just wanted to highlight behavior if in some instance we wanted to load our material. Say we wanted to load it up to a stress of 130 KSI, and we decided to unload it. We would be unloading, that's not what I wanted, so freehand it. We would be unloading at our same modulus of elasticity for our linear elastic curve. And we would have a permanent set or a permanent strain in our material, right, wherever we hit our strain line or our x-axis. If we decided to reload that same material, we would come right back up this curve till we hit our original stress strain curve, and we would follow that off until ultimate failure, or we decided to unload. So you can imagine if you're looking at a spring, right? A spring, we don't want permanent deformation, right? And the spring in, say, the rear suspension of a mountain bike or a dirt bike, or the coils on a car, right? We're constantly putting stress, inducing stress into those coils, right? Putting in deformation, right? They absorb, and so they want to essentially stay elastic. So we want them to stay in this linear elastic region, right? We don't want to permanently deform them. We don't want to go over a bump and then all of a sudden that spring gets half an inch shorter. Then we go over another big bump and it gets another half inch shorter. Pretty soon we have no suspension at all. Okay, so we want it to constantly travel, right, along this linear elastic region. We also know that the energy absorbed, or the toughness of our material, is the area under the curve. So we want this area to be very, very large. Right? Well, in order to do that, we've got two options. Right? You could either make a really tall and steep triangle or a very long and short triangle, right? What does that mean? Well, your modulus of elasticity is either smaller, right? So your spring isn't very stiff, but it can undergo a lot of deformation before it yields, right? But if you wanted a stiffer spring, maybe you have size constraints, right? So you want a large spring constant, or what they would call, 1 inch of deformation gives you, say, 100 pounds. That would be your spring constant, so pounds per inch of deformation. Right? If you really wanted a really high spring constant or high stiffness or a high linear elastic line here or high modulus of elasticity, then you would have to have really a high yield strength, right? This one would have a lower yield strength, right? But it would have a higher yield strain compared to the other one. So there's trade-offs depending on the material you use. And it's incredible that you can get all of this information from just creating one specimen and pulling it apart and conducting the tension test. All right. One last item we'll talk about here is Poisson's ratio. Okay, so Poisson's ratio, we talked about it a little bit. Well, its definition is negative epsilon latitude versus longitude. What does that mean? Well, if this was our original specimen and we decided to pull on it, okay, right, with force P, we're going to get some sort of longitudinal strain, right? This would be this way. And we would get some sort of lateral strain. Okay, so look at lateral strain. Okay. So we'll say when you pull on a bar, right, we add stress. So when we add stress, the bar elongates. Right, this is longitudinal strain. When we do that, okay, the bar also contracts in cross section. What is that? Well, that's our lateral strain. Most of the time, Poisson's ratio is 0.25 to 0.33, somewhere in there. Our largest possible ratio is 0.5. Well, that's because that's rubber. Right, you take a bouncy ball, you step on it. Right, what does that mean? Well, that means our lateral strain is essentially half the longitudinal strain. So if you pull on a piece of rubber and you elongate it 1 inch, well, it's going to get smaller by ½ inch. Why do we care about this? Knowing longitudinal strain, you can calculate lateral strain, or essentially the expansion and or contraction of elements. What does this mean? Well, we can figure out the expansion of rods in compression. Right, if you had a steel column, a steel post, say in a bike frame or a motorcycle frame, something like that, and you can figure out what the longitudinal strain is, well, you can then back out what the lateral strain is. One behavior that it lets us calculate also is based on a tension test, right? We can get our modulus of elasticity, knowing what our Poisson's ratio is, make that better. Knowing what our Poisson's ratio is, we can figure out what our shear modulus is. Or really our shear stiffness. And we'll work through some of that here. It's essentially the same thing as modulus of elasticity, right? But modulus of elasticity is a longitudinal, kind of a normal stress, strain relationship. When we talked about shear stress, well, we have this idea of shear modulus. Well, our shear modulus is a function of our Young's modulus or our modulus of elasticity and our Poisson's ratio. Okay, that is it for today. I will see you guys on Friday in person in class. Yippee.